Hi, I am Dr. Abhishek Joshi, and in this video lecture I am going to discuss about the dispersion modified single mode fiber and the polarization and the fiber birefringence. So these three topics we are going to cover in this lecture. So let's start with the dispersion modified single mode fiber. So it is possible to modify the dispersion characteristics of a single mode fiber by tailoring of the specific fiber parameters. So the major trade-off which occurs in this process between the material dispersion and the waveguide dispersion may be expressed as, that is dt, that is the total dispersion that is given by the material dispersion and the waveguide dispersion. So material dispersion, as we have derived in our previous lecture, that is given by lambda by c d2 n1 by d lambda square minus, and the dw is given by n1 minus n2 by lambda c vd square vb by dv square. So this is the material dispersion and the waveguide dispersion. So at the wavelength longer than the ZMD, that is zero modified dispersion, that is point in most common fiber design, the dm and dw components are of opposite sign and can therefore be made to cancel some longer wavelength. Hence the wavelength of zero first order chromatic dispersion can be shifted to the lowest loss wavelength for silicate glass fiber at 1.55 micrometers to provide both low dispersion and low loss fiber. So this may be achieved by such mechanism as a reduction in the fiber core diameter with the accompanying increase in the relative or fractional index difference to create so-called the dispersion shifted fiber. So it is also known as DSF. However, the design flexibility required to obtain the particular dispersion attenuation mode field diameter, that is also known as the spot size. So band loss characteristics has resulted in specific different refractive index profiles for these dispersion shifted fibers. So the alternate modification of the dispersion characteristics of single mode fiber involves the achievement of a low dispersion windows over the low loss wavelength, that is ranging from 1.3 to 1.6 micrometers. So as we can see in the figure, we are having the dispersion on the y-axis. On the x-axis we are having the wavelength that is ranging from 1 micrometer to 1.7 micrometer, and we can see the standard single mode fiber that is optimized at 1.3 micrometer have the zero dispersion at this wavelength, that is 1.3 micrometers. In case of the dispersion flattened fiber, this dispersion characteristic we can see it is approximately 0 from 1.3 to 1.6 micrometer of wavelength. It is also known as dispersion flattened fiber. And in the case of the dispersion shifted fiber, the standard single mode fiber, the zero dispersion is shifted from 1.3 to 1.55. So these are known as DSF, that is dispersion shifted fiber. So now let's discuss about the dispersion shifted fiber. So a variety of the single mode fiber refractive index profiles are capable of modifications in order to tune the zero dispersion wavelength point, that is lambda naught, to a specific wavelength within the region adjacent to GMD points. In the case, the stepped index profile is illustrated in the figure, that is shift to longer wavelength by reducing the core diameter. So core diameter and increasing the fractional internal difference, that is delta, where the core diameter is given by n1. So typical values are 4.4 micrometer and delta is given by 0.012. So in this figure, as we can see, here we have the refractive index profile for the step index dispersion shifted fiber given by the solid line. So in this, the refractive index profile we can see, that is for the step index DSF. Now this dashed line is a conventional profile. So these profile can be tuned such that we can have the index profile that is having the difference given by del n. So here we have the cladding refractive index given by n2 and core refractive index given by n1. So there are different profiles, that is a refractive index profile for the gradient index dispersion shifted fiber, that we have the triangular profile, next is the depressed cladding profile, cladding triangular profile, and the Gaussian profile. So these profiles are used such that we can shift the dispersion of the fiber. So that is from 1.3 micrometers to 1.6 micrometer or 1.3 micrometers to 1.55 micrometers. So depending on the shape of the profile, we can shift the dispersion characteristics of the fiber. So in the dispersion shifted fiber, we are having the more advanced refractive index profiles for the dispersion shifted fiber. That is, the first one is the triangular profile multiple index. So this one is the triangular profile multiple index. Next is the segmented chord triangular profile. Then we have the dual shaped chord design. So these are the three refractive index profile for the dispersion shifted fiber. So here we can see we are having the maximum refractive index N1 at the center, then we start in a triangular decrease, then we have the step that is N2. Similarly, we have the N1 here, N2, here we have the center core that is N1 and cladding having the N2. So this is the dual shaped chord design. So these are the three designs that can be used for the dispersion shifted fiber. So now let's discuss about the dispersion flattened fiber. So what is the dispersion flattened fiber? The original W fiber structure are initially employed to modify the dispersion characteristics of single mode fiber in order to give the two wavelength of the zero dispersion, as we have seen in the figure in the previous slide, as you can see here. So a typical W fiber index profile, that is a double clad, the first practical demonstration of the disperse flattening using the W structure are reported in 1981. However, the drawbacks of W structural design include the requirement for the high degree of the dimensional control as to make the reproducible DFF comparatively high overall fiber loss, that is from 0.3 decibels per kilometer, as well as very high sensitivity to fiber band losses. The last factor results from the operation very close to the cutoff of the fundamental mode in a long wavelength window in order to obtain a flat dispersion characteristics. To reduce the sensitivity to band losses associated with the W fiber structure, the light which penetrates into the outer cladding area can be retrapped by introducing a further region of the raised index into the structure, and this approach has resulted in a triple clad, that is TC, and quadruple clad, that is QC structure, shown in the figure, that is figure B and figure C, as you can see in this figure B and C. So independent but similar program produced the segmented core, that is DFF design. So all the reports of the low attenuation, that is 0.19 decibels per kilometer for the dispersion flattened fibers at a wavelength of 1.55 micrometers proved difficult to balance the performance attributes of this fiber type. So as we can see in this figure, we are having the three dispersion flattened fiber refractive index profile, that is the double clad fiber. This one is the double clad fiber, that is also known as W fiber. Next one is a triple clad fiber, and the third one is a quadruple clad fiber. So in this, the cladding, here the cladding are changed. In the previous cases, we have seen that the core refractive index profile are changed, but in these cases, all the three cases, we are changing the cladding profile. So most recent effort has been focused on the DFF, that is dispersion flattened fibers, that exhibits low dispersion slopes in the C band, which also provides acceptably large effective core areas in order to reduce the fiber nonlinear effects. So it is particularly difficult, however, to realize both non-zero dispersion slopes and large effective core areas, while in addition reducing their current band loss sensitivities. Furthermore, there remain some fundamental problems associated with the dispersion flatted fabrications, as the chromatic dispersion characteristics as highly dependent on the changes in the fiber structural parameters, including the core diameter and the refractive index difference. So it is therefore still a concern that commercially production of DFF will require both substantial stability and controllability of the fiber process. Hence, such fiber have yet to find the widespread deployment in the telecommunication networks. So next one is the non-zero dispersion shifted fiber. So in the non-zero dispersion shifted fiber, also known as NZDSF, is sometimes simply called the non-zero dispersion fibers, that is NZDF, and the variant of this fiber is having the negative dispersion fiber. So the negative dispersion fiber, where instead of the broadening of the pulses, we are getting the narrowing of the pulses. So that is known as the negative dispersion fiber. So let us discuss about the chromatic dispersion in picoseconds per nanometer per kilometer. So first one, we have the single mode fiber. So here we have the standard single mode fiber given by this curve for the band, for that is original band, extended band, short band, conventional band, L band and U band from O to U. So here we have the non-zero dispersion shifted fiber. So it is having the profile which is approximately close to 0, and the negative dispersion fiber, and in the negative dispersion fiber, the entire region, the wavelength ranging from 1.4 micrometer to 1.6 micrometer, the value is negative. So here we can see, instead of here we are getting the very broad pulses, here we are getting the narrowing pulses. So in the non-zero dispersion shifted fiber, we can observe that is a chromatic dispersion in picoseconds per nanometer per kilometer. The value is ranging from 20 to minus 300 picoseconds per nanometer per kilometer. Here we have the dispersion shifted fiber, that is the standard single mode fiber plus the DCF, and we have the standard dispersion shifted fiber that is at 1.3 micrometer of the wavelength. So it is having the 0 value of dispersion. In case of the dispersion compensating fiber, so in dispersion compensating fiber we are having the negative dispersion, means narrowing of the pulses we are getting, but the combination of the standard single mode fiber and the dispersion compensating fiber, it is having the 0 dispersion at 1.55 micrometer, that is the conventional band. The single mode fiber dispersion characteristics, comparing the profiles for the non-zero dispersion shifted fiber, that is NZDSF, and the negative dispersion fiber, that is NDF, with the standard single mode fiber, that is SSMFF, and dispersion compensating by using the negative dispersion compensating fiber, DCF. So in this figure, we can see that it is typical refractive index profile for the non-zero dispersion shifted fiber, that is NZDSF, and this is for the negative dispersion fiber. So these refractive index profile can be chosen such that we can create these negative dispersion fiber and the non-zero dispersion shifted fiber. So here we have this N1 and we have this N2. With respect to the radius, the values are varying. Now the next is the nonlinear effect. So usually the light waves or the photon transmitted through a fiber have the little interaction with each other and are not changed by their passage through the fiber, except for the absorption and scattering. There are exceptions, however. arising from the interaction between the light waves and the material transmitting them, which can affect the optical signals. So these processes are normally referred to as nonlinear effects or the phenomena because their strength typically depend on a square of the optical intensity. Hence, the nonlinear effects are weak at low powers, but they can become much stronger at high optical intensities. So this situation can result either from the power is increased when it is concentrated in a small area such as the core or the single mode optical fiber. There are two broad categories or nonlinear effects that are separated based on the characteristics, that is the scattering. So scattering is also nonlinear, and another one is the Kerr effect. So these fiber nonlinearities are identified in the figure as we will discuss in the next slide. The fiber attenuation associated with the nonlinear scattering, but these are the Kerr effect shown. So they employed in the important application for the single mode fiber, including the distributed in fiber amplification, wavelength conversion, multiplexing, demultiplexing, and pulse regeneration, optical monitoring, and optical switching. So as we can see, there are different scattering effects. These are also nonlinear effects and the Kerr effect. So scattering effects are classified as the stimulated Raman scattering and the stimulated Brilliance scattering, as we have discussed in my previous lectures. And now in the Kerr effects, we are having the three effects, the basic effects, that is the self-phase modulation, cross-phase modulation, and four-way mixing. All these effects are known as the Kerr effect. So this is a block diagram showing the fiber nonlinear effects. Now, next important thing is the polarization. So cylindrical optical fiber do not generally maintain the polarization state of the light input for more than few meters, and hence for many applications involving the optical fiber transmission, some form of intensity modulation of the optical source is utilized. The optical signal is thus detected by the photodiode, which is insensitive to optical polarization or the phase of the light wave within the fiber. Nevertheless, the systems and the applications have been investigated which could require the polarization states of the input light to be maintained over the significant distances, and the fiber have been designed for this purpose. So these fibers are single mode, and the maintenance of the polarization state is described in terms of the phenomena known as the fiber birefringence. So we are having the phenomena of fiber birefringence. Let's discuss about the fiber birefringence. So single mode fiber with nominal circular symmetry about the core axis allows the propagation of two nearly regenerate modes with a orthogonal polarization. They are therefore bimodal, supporting HE11, HE11Y modes, where the principal axis X and Y determined by the symmetry elements of the fiber cross section. Hence, in an optical fiber with an ideally optimal circular symmetry core, both polarization modes propagate with the ideal velocities. Manufactured optical fibers, however, they exhibit some birefringence resulting from the difference in the core geometry, resulting from the variations in the internal and external stresses and the fiber bending. The fiber therefore behaves as a birefringent medium due to the difference in the effective radius indices, and hence the phase velocities for both these two orthogonal polarized modes. These modes therefore have different propagating constants, that is beta x and beta y, which are dictated by the anisotropy of the fiber core. So in this case, we have the beta x and beta y are the propagation constants for the slow modes and the fast modes respectively. When the fiber cross section is independent of the fiber length L in the z direction, then the modal birefringence BF for the fiber is given by, so modal birefringence BF is given by, that is beta x minus beta y divided by 2 pi by lambda, which is k, and k where lambda is the optical wavelength, and light polarized along the one of the principal axis is retained its polarization for all L. The difference in the phase velocities causes the fiber to exhibit a linear retardation, that is phi z, which depends on the fiber length, that is L in the z direction, is given by, that is phi z is given by beta x minus beta y by L, assuming that the phase coherence of the two modes components is maintained, and the phase coherence of the two modes component is achieved by the delay between the two transit times less than the coherence times of the source. The coherent time of the source is equal to the reciprocal of the uncorrelated source frequency width, that is 1 by del f. So it may be shown that the fiber bifringence, that is coherence, is maintained over the length of fiber, that is LBC, that is coherence length. So LBC is equals to C by Bf into del f, that is lambda square by Bf into del f, where C is the velocity of the light in a vacuum and del f is the source line width. So as we can see in the fiber bifringes, we are having the polarization of the vectors, where we can calculate the beta x minus beta y into L equals to 0 in this case. So as we have when the phase difference is pi by 2, we are having the circular polarization. When phase difference is pi, we are getting this direction of the arrow. When we have 3 pi by 2, we are getting the circular polarization. So we are having the illustration of the beat length in a single mode optical fiber, and the polarization states against the phi z, that is the phase difference, and the light intensity distribution over the beat length within the fiber. As you can see here, we have the beat length, that is for L8, and this is the z-axis. So when the observer observes here, so we have the observer which is observing the light. So however, the phase coherence is maintained over the coherence length and leads to the polarization state, which is generally elliptical, but which varies periodically over the fiber. So this situation is illustrated in the figure, where the incident linear polarization, which is at 45 degree with respect to the x-axis, becomes circular polarization at phi equals to pi by 2, and the linear again at phi equals to pi. The process continues through another circular polarization at phi equals to 3 pi by 2 before returning to the initial linear polarization at phi equals to 2 pi. The characteristics length, that is LB, for this process corresponding to the propagation distance for which a 2 pi difference, that is phase difference, accumulates between the two modes, is known as the beat length. So beat length can be calculated using the formula, that is LB, that is equals to lambda by Bf, and we know the formula of the Bf as we have discussed here. It is nothing but beta x minus beta y by 2 pi by lambda. So if we are substituting Bf, which results as the beat length, that is LB equals to 2 pi by beta x minus beta y. So it may be noted, it can be directly written as the phase, that is LB, for the beat length, that is given by beta x minus beta y into LB, that is equals to 2 pi. So in a perfect fiber, various perturbation along the fiber length, such as the strain or the variations in the fiber geometry composition, lead to the coupling of the energy through one polarization to the other. The perturbations are difficult to eradicate such that it may easily occur the fiber manufacturing and the cabling. So we can have the energy transfer is maximum when the perturbations have the period corresponding to the beat length. It is given by period, that is equals to lambda by Bf. However, the cross polarization effect may be minimized when the period of the perturbation is less than the cutoff period. So we have the cutoff period given by and hence the polarization maintaining fiber may be designed by high bifringes, that is large bifringes, that is a maximization of the fiber bifringes, which is may be achieved by reducing the beat length, that is LB, to around 1 mm. And then we have the low bifringes, that is a minimization of the polarization coupling perturbation through the period, that is the period, and it may be achieved by increasing the cutoff period, that is giving a large beat length of around 50 meters. So the beat length in a let's discuss one numerical based on the fiber bifringes. So beat length in a single mode fiber, that is given by 9 centimeters, and the light from an injection laser with having the spectral line width of 1 nanometers and the peak wavelength, that is lambda, and is launched into it. Determine the modal bifringes and estimate the coherence length in this situation, in addition to calculate the difference in the propagation constant for the two orthogonal modes and check the result. So find the modal bifringes. We are having Bf, that is given by lambda by Lb. So lambda is given by 0.9 micrometer, so 0.9 micrometer, and the beat length is given by 9 centimeters, so 9 centimeters 0.09, we are getting 1 into 10 to the power minus 5. So similarly, the coherence length can be calculated as lambda square by Vf into del f, so we are getting 81 meters. So we can calculate the delay difference, that is beta x minus beta y, that is equals to 2 pi by LB, so we are getting 69.8. So this may result checked, that is beta x minus beta y is nothing but 2 pi bf by lambda. Substituting the value, we are getting 69.8, which is exactly same. So there's one more numerical. So two polarization maintaining fibers obtaining at a wavelength. So we are having a wavelength that is lambda given by 1.3 micrometer, have the beat length that is LB, that is 0.7 and 80. So there are two beat length. Determine the fiber birefringence in each case. Comment on the result. So we have the formula of the beat length that is given by lambda by LB. So substituting the value, we are getting 1.86. At the beat length for 80 meters, we are getting 1.63 into 10 to the minus 8. So which actually indicates the low fiber birefringes. So in this video lecture, we have discussed about the dispersion modified single mode fiber. Then we have discussed about the polarization and concluded with the fiber birefringes with a low and high fiber birefringes. So here we are going to stop the lecture. Thank you.